Welcome, EECS16A. Woo!
You did really well. See, you're selling yourself short. Okay. Oh, Div, no Mickey today. Do you want to walk around? Yeah? Thank you.
Damn.
You arrived right on time. Thank you. How is everybody doing? Woo! Very good. I have a small announcement. Today I cannot be in office hours because I'm giving a talk, a research talk immediately after this class. But one of our very experienced TAs, Anvita, is going to be there to answer questions. If you are planning to go to office hours after class, I'm sorry that I'll not be there, but Anvita will be there, and she knows everything about this class. She has been on staff for many, many years, so still go. And then if you really wanted to talk to either me or Mickey, then just write me an email and I'll make a separate office hours to talk to you, okay? Sorry about that. And Mickey is not available. Mickey is out of the country, so yeah. He's in Korea, so he will not be in office hours or here, but we are. Okay, so today we are going to continue talking about operational amplifiers. This feedback is really annoying. Okay, I will give you a lot of examples for operational amplifiers that are used for different applications. So far, we have used the operational amplifier as a comparator to compare two signals and give us a binary answer. And then last class, we were just finishing the design for a party, right? For an audio where we wanted to get amplification of a signal in order to play music loudly. So we were dealing with the problems of too much amplification, which is what I'm getting here. I'm going to try to mitigate this problem. Better? It's better, right? Yeah, but you can still hear me. Okay. Div, can you hear me? Great. Today I want to finish that very quickly and then do one example after an example after an example after an example about operational amplifiers and the types of operations that they do, or they can do. They can be set up to do. And then next Tuesday, we're going to talk about design in a more formalized way, which is one of your notes, design. But ever since we start doing resistive touch screen, I've been talking to you about design, right? Always thinking, which block should we put here? How should we model this block? How would the behavior be? So in our last lecture of this module, we're going to formalize the design methodology. Bless you. Okay, so we were here last class where our problem was, first, we wanted to play music very loudly. Music was a digital signal. We want to drive an analog device, a speaker, and we needed a new component that would do that conversion from digital to analog. So we learned about digital to analog converters. Then we saw that by putting the digital to analog converter in the middle of the speaker and the digital signal, we got a loading effect where the voltage output of the deck, or the voltage output getting to the speaker, was actually lower than the voltage that we were giving to the deck, or lower than the signal was. So that was a problem. And we were like, okay, nice try on the design, we need to change things. Let's get rid of the loading effect by isolating the deck from the speaker. And then we start looking at about operational amplifiers, or what we could add to the operational amplifier. in order to isolate. We also, but then the operational amplifier was operating too much, amplifying too much, and we got a distorted signal, right? Or we were having such an amplification that the output was going to the rails, right? And what are the rails? The rails are the set voltage sources that we add to the operational amplifier such that we don't get an output of 100,000 volts, right? Because we know that the gain of the amplifier, at least an ideal amplifier, is infinite, really, really large. Then, next on our design was, okay, let's change this operational amplifier to try to control the gain. And that's when I taught you negative feedback. Negative feedback, then it's a signal that you add to the loop and you feed your operational amplifier with that signal, and that signal is a portion of the output, and by feeding that portion of the output back into the operational amplifier, you can correct course, right? And then the idea would be, okay, if I am standing here and somebody is to push me, I'll try to correct so I don't fall. That's negative feedback, right, in a system. There, in a system of the amplifier, if you don't want your amplification to go to the rails of the amplifier, you need to make sure that you control the output. So we give a little correction to the system so that you get the amplification you want without railing your system. That's where we were. And then we finished by saying, okay, if we use this operational amplifier in this configuration, where we used our good old voltage divider as the component that is going to be providing the negative feedback signal, we can take a portion of the voltage, because we know that the voltage divider divides the voltage, feed that into the amplifier, and then we went through all the calculations and the circuit analysis to show that we can get to a point where the gain of our system that we define AV here, V out over V in, can be controlled by the ratio of those resistors, which for us as designers is a powerful tool, because now if we know the gain that we are targeting, and we know we don't want infinite gain, it's pretty useless unless you are just using as a comparator. So if you know the gain that you want, you can now pick those resistors to give you the ratio that is desired for your system. In our case, we wanted something that would be compatible with the DAC, which had voltages from 0 to 3.3 volts. And we wanted to be feeding that signal to the speaker, which was 0 to 10 volts. So anything between 0 and 10 would be good for the speaker. So we said, okay, if we get, in order to get a gain of 3, which would be good for this system, since we're using the DAC, then we would have a voltage that is between the range that we wanted for the speaker. Then we would pick these resistors such that the ratio between R1 and R2 would be 2 plus 1, then it would give us a gain of 3. We stopped here because I wanted your full attention for what comes next. So next, we are going to derive the two rules that are quite well known for operational amplifier, and they are called the golden rules of operational amplifier. Why are they why are they called golden rules? Somebody once asked. I don't know. My guess would be because they're precious, they're very useful, and this example that I'm giving you here is a perfect example to get to the derivation of the golden rules. So I'll pick up from where I stopped, which was here. We used KVL mostly, to get to these equations that we're relating voltage differential. In this case, well, not in this case. We defined voltage differential as the difference between U plus, the potentials U plus and U minus. We used, so that was voltage definition, and we got that because U plus was connected to V in and U minus was connected to voltage feedback, then that means that VD, voltage differential in the amplifier, would be V in minus V feedback. We got that V out, which is the voltage that you're measuring here, outside of your circuit, is connected to the operational amplifier. And we know that inside of the operational amplifier, we have this block here, which is a voltage-controlled voltage source that is given by A, which is the gain of the amplifier, ideal amplifier, infinite gain, times VD, which is this voltage differential. So V out is also related to V in and V feedback, which makes sense, right? That's what we were going here with our design. And then finally, we found that V feedback, which is the voltage that we are feeding here into the terminal U minus, is given by the voltage of this block that we put here to give you that feedback signal, which is the voltage divider, which we knew how to derive because that's like an old tool that we use all the time. Yeah? Okay, then I did substitutions just to get us to an equation that shows what would be the ratio between V out and V in, which will give you the gain of the system, the gain of everything here, the way we connect things. Okay, not only the amplifier, but the entire circuit, the way we connect it, would have a gain that is given by this, okay? Which we found that when A is infinite, because we have an operational amplifier there, that gain will be given by the ratio of the resistors. Beautiful. Okay, now that we are fresh in our memories, I'm just going to continue this derivation to get to very, very handy rules here for us. So one of the equations that we had from before here is that V out is equal A, operational amplifier gain, times VD. So here I'm just writing equation 2 differently by isolating VD, voltage differential, as V out over A, okay? We know from previous slide, previous class, that V out, which we derived here, is given by A over 1 plus AF, where F is this term that we gave for feedback, right, times V in. So now let's do a little bit of interpretation of the meaning of these equations. First, I'll just write VD now in terms of V out, which would be 1 over A, because it's V out divided by A, times V out. And V out is A over 1 times AF times V in, right? That means that the voltage differential is going to be given by V in over 1 plus A times F. F was the feedback signal. Okay, if we are dealing with ideal operational amplifier, so I'm going to say here, if we have an ideal operational amplifier, what's A? Infinite. If A is infinite, what happens to VD? 0. Okay. Now, watch this. What is VD by voltage definition? VD, which is the differential, is U plus minus U minus. If VD is 0, that tells us that U plus is equal to U minus. Okay, this is golden rule for operational amplifier number 2. Number 2. This is the second golden rule for operational amplifier, which is, oh, pay attention to the ifs, right? If you have an ideal operational amplifier, the gain is infinite. So in that case, you're going to assume that U plus equals to U minus. That can be very handy in circuit interpretation, because when you're doing the analysis, oh, what happens if U minus is connected to ground? You know that U plus is 0. Very, very important and very handy. In practice, that's not going to be the case. There will always be a little difference between the signals, because there is no ideal device, just like there's no ideal person. But we can simplify our lives by considering, for the engineering purposes, that U plus is equals to E minus. At the very beginning, when I introduced operational amplifiers to you, I said that the model that we were going to use for the operational amplifier was an open circuit, right? Where you have U plus and U minus here, and you have an open circuit, because those are the leads that you're connecting somewhere, which had a very important implication. Let me put the operational amplifier here, just visualization for now. And I'm going to put dotted, because, you know, that's how we have been doing this. Okay, so there's our operational amplifier. So if I had to do a current analysis for the operational amplifier, we would have an I plus and an I minus. We don't care about directions, right? We know that we can get the right thing. But what we do know is, because we are using a model of an open circuit, that tells us that I plus is equal to I minus, which is equal to 0. Thank you. Because in the case of an open circuit, the current is always 0. Okay, this is the golden rule of operational amplifiers, number 1. Okay, and we did use this from day one, but I didn't call it golden rules just because, you know, there's time for jargon. After the learning, you can use jargon. We're going to use this over and over today, okay? So, I plus equals to I minus equals to 0, always, always the case, okay? U plus equals to U minus if ideal amplifier and amplification to infinite. Yeah? Go ahead. Question, Div. Right here. Keep running.
So, oh wow, that's loud. Okay, so if there's no current flowing through the op-amp, then does like the op-amp not affect V in, like whatever, or things that are connected?
There are different things, right? We are doing a model, just like we have a voltmeter. When you have a voltmeter, remember the model that we said. The model for the voltmeter was an open circuit. Is there current going through the multimeter? Absolutely, inside the multimeter, right? But those leads there, you model as an open circuit. Will the operational amplifier pull current? Yeah, yeah. If you wanted to do analysis to every single transistor, resistor that is inside the operational amplifier, there would be current. But in our model, we use an open circuit. Go ahead.
Does the golden rule number 2, is it only in effect when you have a negative feedback loop? I would assume.
Yes, also that. Yes, thank you. Because that was the first thing that we did when I introduced this. Thank you. Yeah, I forgot to put it there. So negative feedback and ideal amplifier. Great. Let's just close the loop on our design of playing music. Let's see what's going to happen now. Oh, yeah.
If U plus equals U minus and U minus is just V out by negative feedback, does that mean that V in equals V out? Or where am I mistaken?
Oh, in this circuit, let's see.
Yeah.
If we say U plus equals to U minus, and we said that U plus minus U minus was V in minus V feedback, that means that here, now that we know the rules of the amplifier, and I told you that it was in negative feedback, you can say, okay, then that means that V in equals to V feedback. Thank you. Very good. Okay, in our design then, we had the DAC, digital to analog converter, which we modeled as a voltage source here that was giving a signal. We used the Thevenin to model the DAC as a voltage source that is giving you a signal, and a resistor, which was the R Thevenin, or you can call R DAC, since we are using that to model the DAC. Then, if we take this non-inverting amplifier, which is the name of this amplifier that I gave you here. Why is non-inverting? It's because it's not inverting the signal, the polarity of the signal. And we pick R1 and R2 to have these ratios. We are going to have a feedback gain of 3. And then, okay, if we have, by getting the feedback gain of 3, we can operate our speaker that operates between 0 and 10. Yay, party. Okay? So we went a long way around, bring lots of tools to come here. I'll come back to this at the end of class again with another solution that might be even simpler. But first we'll learn more. So today, my friends, I give you a nice table that you can print for midterm 2. Yeah, with all the operations that we are going to learn. So far, from this table, you have voltage divider. Here's the nice formula for the voltage divider. We are going to do voltage summer today in a very cool application, unit gain buffer, inverting amplifier, non-inverting amplifier, we got it. And we are also going to do the trans-resistance amplifier. Cool? Yes, okay, what's different here from what I have done? You see that here, this table is more complete than some of the examples that I gave that I just put U minus and ground. Here, our U minus or sometimes BDD or VS, there's always a reference here when it's appropriate to put a reference. So that will give you more tools, and if you connect, instead of connecting to a reference, you connect to the ground, then you know that that terminal there or this term on your formula is 0. Okay? Question?
How does a digital to analog converter work?
I explained like 2 classes ago, so try to watch the lecture if you still have doubts. But it basically, it goes through a bunch of resistors that would then change the signal, and then it goes through an amplifier that gives you, takes the digital and it gives you an analog answer. But 2 lectures ago you have that. I even put like the circuit diagram for it. Lots of resistors, taking each beat goes through a resistor. Okay, I just have to keep going with the content. Yeah.
Oh, just wanted to ask, should we try to memorize these, or do you just Google it every time?
I'm sorry, should you try to?
Should we try to memorize it, or do we just Google it?
Oh, no, don't memorize. Please learn how to analyze. And you know that our midterms are open book, right? So you just cannot use the internet, but you can print this out.
So the U in and U out for an operational amplifier, are they just references, or does the op amp get power from U and a U plus and U minus, or does it get power from VDD and VSS?
Oh, very good question. Where does the power come from? There is, sometimes you can connect one of the U plus or U minus for power, and the VDD and VDS also could be used. Typically, they are the same, VDD and VDS, so you can give the same voltage there. Yeah, but in our examples here, we're using either U plus or U minus, and as the power or as the signal to the amplifier. What's going to make the amplifier turn on? Okay, there is an overall power for the system. So if you look at your board, you will have an operation amplifier that's power from the outside. The signal that comes in comes from U plus or U minus. Great question. Okay, shall we do this? You had this in discussion yesterday, right? But let's do this again here, which is the methodology of how do you check if you have negative feedback in a operational amplifier. So you were given 2 steps that you have to follow. The first step would be when you want to see if, why do you want to see if an operational amplifier is a negative feedback? Because then you know that golden rules apply. Golden rules apply, life is easy, right? So the first step is you will zero your the independent voltage sources, right? So you zero your power sources, and then you look at the circuit without that. So in this case, I'm going to do this together with you. If I had to zero this power source, I can redraw the circuit without it. So I will have, I'll have the ground here. And in this node where I had the power source, what element do you use when you zero a power source? A wire, thank you. And then you will have R1. And then R1 was going into an operational amplifier. And we had another resistor here, R2. And this was U plus. U minus is going to ground. Okay, U minus going to ground. Then we have V out here. Resistor connected this way. And then we would measure V out here, knowing that this is also grounded. Okay, in the diagram that I took from your notes, the currents are already labeled. So if the currents are already labeled,
the op-amp labeling, shouldn't that be negative on top and positive on the bottom, just like the drawing?
oh yes, thank you. It should. Oh, my eraser is too big. Thank you for paying attention. We were going to run into problems if you didn't tell me. Okay. Now, we have U plus and U minus. Okay. Good. Then, thank you. Then in the diagram here, this node here was called U2. And then we have this node here called U3. And there were currents labeled I minus and I plus, going this way. We had I2 here for resistor 2. And of course, we also had I1 coming out of resistor 1. Okay, let's see. Let's test our skills now. So, second step. The second step to check if you have negative feedback is you would wiggle a little bit the output. Why do you wiggle the output? Because you want to see that if the output increases, what happens to the signal in the incoming signal. So you want to see if when you wiggle the output a little bit, what is your amplifier going to do? Is it going to increase further your output, or is it going to correct and decrease the output? So you have to go with your intuition and what you learned so far. And you have to remember that inside this operational amplifier here, this little triangle, you have an independent voltage-controlled voltage source, right? So right here, you have an independent voltage-controlled voltage source that is given by A times U plus minus U minus. And you're going to use this a lot because you want to see what's happening to that term, U plus or U minus, as you wiggle the output. Okay? So let's do this. So first step, we completed. We drew our circuit without the voltage source. Now we are going to wiggle the output and see how the system responds. So right here on node 3, where my output is, I'm going to increase. Okay? So I'm going to increase the output by a little bit, just to see what happens. Now, if I increase the output, I want to see what's happening in this terminal here, right? Because U3 is connected to U2. So I want to see what's going to be happening here, which by connection is also related to U minus. So in this diagram, when I change the output at node U3, I want to see what's happening here on node U2. So if I measure the voltage here at U3, what's going to happen to voltage at U2? Take a moment to think and then tell me, does it increase or decrease? Good form.
The voltage would increase at U2 relative to ground?
Why?
Well, the voltage increases at U3, and so there's a voltage drop across R2, but the voltage on one side of R2 is higher, so like U2 would also increase, I guess.
Yep. Thank you. That's exactly right. Because the way it's connected, so if I increase the voltage at the point U3, then right here, where I have U2, it will also increase. Okay. Now, if I increase the voltage at the point U2, what's going to happen to my new V out? Is it going to be higher or smaller?
It would decrease because the voltage connected to U minus is higher.
That's right.
And
Very
so,
good. How do we know this? Well, if we are increasing U3, and U3, you can even forget about this, right? You know how this circuit is working. This is a voltage divider right here. So if you increase the output, you're going to increase the voltage in the middle too. Even though you know the voltage is dividing, but it's going to be increased also because because U3 is increased. So when you increase U3, you increase U2, which is connected to U minus. Now, inside the amplifier, you have the voltage differential, which is U plus minus U minus. So if U minus increases, that means that your output, which is U plus minus U minus, will decrease. So then U3 will decrease after the feedback, which is what we want. right? So if I am subtracting U minus, and U minus is a larger number, that means that my total will be smaller, right? Which is what we want for negative feedback. Then we say, okay, check this is in negative feedback, and you go, hooray, it's in negative feedback. If it's in negative feedback, that means golden rules apply. And if the golden rules apply, then our circuit analysis is easier. Let's do that. Ready? Questions before I move on? Does anybody see why V plus is, okay, there we go.
Wait, could you just say one more time why
Say one more time, yes.
it was a negative feedback loop?
Yeah. I'll say as many times as it gets, okay? Okay. First thing you have to do, try to visualize the circuit. Yeah, okay. Just take a seat, relax a bit, Dave. Yeah, okay. Try to visualize this circuit without the amplifier, right? Because what I'm doing here is, I want to increase the voltage here at this node, U3. Now, U3 is related to U2 because I have a resistor here and I have another resistor there. Now, if you ignore this amplifier because it's new to you, it might be scary, just ignore that, okay? Do you know what happens when you have just a circuit that is like this, where you have R1 and R2? Where you have R1 and R2. That's the voltage divider, right? So U3 in our drawing is right here. Agree? U2 in our drawing is right here. Yeah? So if I come here and I increase U3, what happens to U2? Increases, right? And then now if U2 increases, that means, okay, now we have to think about the amplifier. So everybody understood here why U2 increases? Yeah? Question, okay.
Like why U2 increases?
That's your question, why U2 increases. Okay, so do you agree? First, let's go step by step. Do you agree that if you ignore the amplifier here, you have a voltage divider? Okay. Do you agree that U3 is here? Do you agree that U2 is here? Okay. In the voltage divider, what's the equation for voltage divider? V out equals R1 over R2 plus R1 times Vs. Okay. If you're going back to voltage divider, right? And I tell you, now V out is higher. Resistors are all the same. What does it mean? That this voltage here is higher. Oh, yeah? Yes. The job of a teacher accomplished. Thank you. Okay. All right. We are together. Okay. Now we go back to the amplifier. And do we all agree that the voltage that we have here at U2 is what we are plugging into our U minus? Yeah? Do we agree? Okay. So if that's U minus, and we know that V out is going to be U plus minus U minus, now we have a higher number. Ooh, no eraser. Now we have a higher number here, which is U minus. So something minus a higher number is something smaller. Yeah? Got it? I got all of you? Okay. One more question.
So if U3 is U3 the error signal or something else? Because if we're increasing U3 and then it turns out
U3 is V out. in our
So in the definition, what exactly is the error signal? Is that you?
the arrow signal by the we have the arrow signal here is U2 by our, but we're not talking about that, right? We're just looking at voltages.
And the output also increases. Isn't that positive feedback? I understand why it's negative feedback, but I'm just confused
It's like
by the definition.
I will increase, okay, I will tweak the output a little bit. I'll say let's pretend that the voltage out is going to be increased. Now let me look at what happens to the voltages in my circuit, which is U2. Then I say, okay, if I increase, if my output is higher, that means that my U2 is higher. Which means that my next V out, right, would be smaller. That's negative feedback. Yeah, it's what happens next. What will happen to your V out with the wiggle that you gave? Thank you. All right, now let's do the analysis. Very important step now. When you do the analysis, you turn on your voltages, okay? Because your analysis is going to depend on the voltage sources. And just to check if we have negative feedback or not, we turn them off. Okay, so because we said it is a negative feedback, hey, golden rule applies, we can even write the golden rules here to help us, which means U plus is going to be equal U minus. Yeah? And I plus is going to be equal I minus, which is equal to 0. Okay, now take a look at this diagram as is, and I'm going to ask you a question. What's U minus? Yeah? Question or answer?
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 Is it 0?
Answer? Is it 0? That was a question.
Oh, 0. Oh, fine. It is 0.
Oh, thank you. That's an answer. It is 0. Why, my friend? Why?
They're equal.
Because U plus is equal. But what tells you that they're equal, U plus and U minus? What tells you that U plus is 0?
It's a negative feedback.
Because it's not because U plus is connected to ground, which is our reference node, which is 0. Very good. Okay. I am going to do, for one last time, the long circuit analysis, okay? Which is the method that I taught you so far. And then we are going to do very fast circuit analysis. Why do we do circuit analysis? Circuit analysis, we want to know voltage out or current out, right? That's why we care. So we are going to try to find out V out by using the method that I taught you so far. So let's do it. I have everything labeled here, currents, voltages. I have the signals right. I copy it right. Okay. Number 1, step number 1. Let's label the voltages from looking at our potentials. What is U1? I count on you, so I know if you're learning or not. What's U1? V in, thank you. What's U2? 0. Why U2 is 0? Because it's U minus, golden rules. Okay, let me put here in gold, golden rules. So nice. Okay, next, what is U3? V out. Woo, first step done. Okay, we got our voltages figured out. Now 2, what's the next thing we do? Elements definitions. Why do we do this? Because that's what gives us the relation between voltage and current, which are our unknowns. We know the resistances. Okay, what elements can we use here? We have resistors. So if I write voltage across resistor 1 will be R1 times I1. Voltage, we have two resistors. Voltage across resistor 2 is going to be R2 times I2. Okay. Let me push you. What's I1? 0. Okay. Keep thinking. I'll get there. That was a short test. We are still doing element definition. Now, let's do voltage definition. Voltage definitions we pretty much did, but let's do voltage definitions here. And why do we do all this? To get the equations that we need to get to the answers we want. Okay, voltage definition. I could apply, let's see, using voltage definition, I can write VR1 equals U1 minus U2. Yeah? Okay, why? Because the resistor is between these two nodes. So U1 minus U2. Okay, what's U2? 0. So what's the voltage here in 1? U1. Voltage across the resistor is U1. Okay, potentials and currents are unknowns. Okay, now next for resistor 2, using voltage definition, which potentials is resistor 2 in between? U3 minus U2. Okay, so what's the voltage across resistor 2? The potential. It's U3. We know that U3 is V out. Okay, we're seeing where things are. Now, let's do KCL. Because we do have unknown currents, right? So let's do KCL. KCL for which node? Which node would be important for us to do KCL? Now, decisions that you should start making when you're doing circuit analysis. Don't need to do circuit analysis for the whole thing, only for what it matters. So is it U1, U2, or U3?
Quick thing he pointed out, it should say VR1 equals U1.
What?
I think you wrote U2.
What did say it again? With confidence, so that I know what I did wrong.
For number 3, voltage def, the first statement, you wrote VR1 is equal to U2, and it should be U1.
Uh-huh. So you mean it should be U1 minus U2?
Yeah.
Because of, because of the signs, yeah. Thank you. Does it matter? In my mind, I did the right thing, so it's hard to see what's wrong. Thank you. Okay, but I think in the notes that I posted, they were right. Yeah? Yeah, they were. Okay, thanks. Love it. It's so much nicer when you guys talk. Okay, KCL. So the question was, what is the node that matters for me to do KCL now? U2. Why? Because we want to figure out what's happening in the amplifier. So if you do KCL for U2, what does it say? Currents that are coming into the node are equal to the currents that are going out of the node. So in that case, what does your KCL equation look like? I1 plus I2, which are coming into the node, equals to I minus. Do we know I minus? Yeah. We know that I minus is 0. Definition of the amplifier. Golden rule number 1. That tells us that I1 equals to I2. Negative I2. You guys are rolling. Great. Next, what do? What we want is find out V in and V out, right? Now finally we have everything that we need to write our gain relationship, V in and V out. So let's go back to the board here. I know that V in is going to be equal U1, which is equal I1 times R1. I know that V out from the equations here that you guys told me is equal U3, and U3 is equal R2 times R2. Oh, where did I get this from? It's because I got so messed up here that I forgot to put this is 0. So VR2 is equal U3, and VR2 is there. Yeah? Everybody follows? I'm going to color my steps here. Okay, VR2 is here. VR2 is equal U3, but VR2 also is equal to the currents because of Ohm's law. So that's what I did there. Okay. Because I was still trying to figure out my mistake from before. Okay. Ready? That means, okay, since we know that I1 plus I2 equals 0, now we can write this in terms of V in and V out, which will give us V in over R1 plus V out over R2 equals 0. That means that V out, once you isolate everything and pay attention to your signals, your signs, is going to be R2 minus V in over R1. But I still want to have a simpler relationship, so I'll just say V out. Just massaging here the equations. It's going to be R2 over R1 times V in. And the nice thing that appeared here is this minus. So when I look at the gain of this amplifier, and the gain AV, remember, is V out over I in, V out over V in, we will get this to be minus R2 over R1. Yeah. So it's kind of different from what we had before. Before I said you had non-inverting amplifier. Now we have an inverting amplifier. So if we had used this with the same, in a system, we could still pick the gain by picking the resistors that we are going to use, but we would flip the sign. Okay? We would flip the polarity of our V out. So pretty cool. Signal comes in, gets amplified, polarity flipped. Inverting amplifier. It's on your notes. Now, who is ready to learn a faster way? Yes. Okay. If you are not there yet, keep doing the long way. Still works, but I think we are ready to at least see a faster way. Same circuit, okay? Same thing. So we are going to check for negative feedback. We say, okay, this is a negative feedback. We already done this. Now, if I know that it's a negative feedback, that means that golden rule number 2 applies. And because of golden rule number 2, I can write u plus equals u minus. Okay. Then I look into my system here. I look at the circuit diagram, which was my first question to you, right? Before I did the long way, you knew the answer already. You said u plus equals 0. So because u plus was connected to ground. So your intuition is there. Because you know that u plus equals 0, and because we checked and it was a negative feedback, that means that u minus equals u plus equals 0. Okay, that's great. Now, because it's an amplifier, we know that the golden rule number 1 also applies. And golden rule number 1 is going to tell you that I1 plus I2 equals I minus, right? We did that. And by golden rule number 1, we found that I minus equals 0. Okay, now you look at your system and you say, okay, I know what I1 is, because I1 is the current going through the resistor. And if I apply current going through the resistor, Ohm's law. So if you do golden rule number 1 plus KCL at the same time, you could write, okay, I1. What's I1? I1 is the current going through the resistor, which is V1 over R1. But V1 is U2 minus U1 over R1. Okay, plus I2. What's I2? I2 is U3 minus U2 over R2. We did this like in all steps. This is equals 0. Okay, we also know that U2 is U minus, which is 0. So if we know that this is 0, this is 0. Oh, no, not that. This is 0. Then we have a much quicker way to get to minus U1 over R1 minus, plus, sorry, what's wrong? No, it's all good. Minus plus U3 over R2 equals 0. Now, from the beginning, when I wrote the voltages, it was very easy for us to know what the potentials are. What's U1? U1 is V in. What's U3? U3 is V out. Those were all the first questions I asked you, so you know that, okay? It's just a different way of writing. That tells me that we can write this as minus V in over R1 plus V out over R2 equals 0. Now I want V out over V1, V in, so there you go. Our answer is right here. V out over V in is going to be equal minus R2 over R1. So much faster. Yeah? From now on, this is what we are going to do. Yeah, go ahead.
Sorry, why is it I1 plus I2 is equal to I negative, isn't it? I1 is equal to I negative.
It's
plus
from
I2.
here, right? Remember when we did KCL? From the circuit, we got this. This I1 plus I2 equals I minus. Because we did KCL to this node, you have I1 coming this way, I2 coming this way, I minus going that way. So the two currents coming in are equal to the current coming out.
I2 is just negative because it's going into the positive terminal. Oh wait, no, I think I'm
I2 was defined, remember how we defined the direction of currents? How do we define the direction of currents? Randomly, and then we use passive sign conventions. Very good. Got it? Great. Okay. Let's keep going. Let's keep going. Second, so this inverting amplifier. Now we are going to use the faster way, okay? I'll take questions later. Let me keep going because we're going to revisit all this. All right, this amplifier. First question I have for you. Is this amplifier in negative feedback? Think. While I draw, I'm going to draw the circuit without the voltage source. Okay? So, and then I expect answers. I will have this connected to my amplifier here. This is negative, this is positive. I don't have my current source. What do I substitute for a current source? An open circuit, yes. Oh, you guys, you really paid attention. That's really good. Okay. And then here I have V out and the ground. Okay. Okay. And R. I will label my nodes here. This is going to be U1 and this is going to be U2. Last. Okay, is it in negative feedback? No? You don't think so? Come on, be confident. Stick to it. I think it's positive feedback. Okay, how do we know? Use the trick. What's the trick? Okay, for the trick we are going to wiggle the output. And then we are going to look at the potentials between that are affected by this. So I can forget about this. And I look here. I have a resistor connecting U1 and U2. If I say that the voltage, okay, what's the voltage definition here for a resistor? So VR is going to be what? U2 minus U1, right? Okay, so if I tell you now to check for negative feedback, I'm making this U2 bigger, what's happening to U1? Increasing, yeah. So U1 increases. Now, U1 is connected to U plus. So what's going to happen to my next V out? Well, my next V out now is U plus minus U minus. If I'm increasing U plus, what's going to happen to my next V out? Increase. So that is positive feedback. What do we do now? Do we have a nightmare of a circuit analysis because golden rules don't apply? No, no. How do you fix this? You go there to your circuit and you say, oh, I connected you wrong. Flip the polarity. Right? We can do that. We can do that. I'm going to flip the polarity, okay? So, why? Because this is an element. It's a physical thing. Copy. Paste. Okay. Now, I am going to come here pick up my element from my board and say, I'm sorry I connected you wrong. And I am going to say, now this is minus, this is plus. Okay. And now we double check, right? Because when things didn't go right one time, we double check the second time. Now I'm going to make U2 bigger. What happened to U1? Increases, okay. Ohm's law still applies, but now my U1 is U minus. So if I am now having U plus minus U minus, and U minus is larger, what happens to V out? Decrease. And if V out decreases, that means negative feedback. Yay, that's what we want. Happiness. Okay. Now let's do the circuit analysis. I turned on back the current source. Yes.
Positive feedback.
Do you ever use positive feedback? Would that work? Can you imagine using a system and positive feedback? Imagine Mickey is an amplifier, and we operate Mickey in a positive feedback. It's like unbearable, right? Same with a speaker. If this speaker has amplification, if it was positive feedback, every time I hear myself, I speak louder and louder and louder. It's just, yeah? Okay. Circuit analysis for this example, which we had there. So, same thing. We checked that there was a negative feedback. If it's a negative feedback, I can write with all the confidence I have that U plus equals U minus. I can ask my students, what is U plus? 0. That means that U minus is also 0. Yeah? And we are going to zoom through this analysis now. Now, let's apply golden rule number 2 and write out the equations in terms of voltages and currents. Okay? So, first, I have a current source. And what else do I have? I have a resistor. So I know that I will use some element definition for my KVL. I will have current and I will have resistor definition. So let's start with the resistor definition for our current here. Okay, so I'm going to do KCL for my node U minus. So through the resistor, how would you write the resistor definition? Here. That's Ohm's law, right? So if you had to write, I'll write here, VR would be equal to R over which current? Over, sorry. Times which current? I. Okay, this current here. Okay. If you had to write element definition for VR, what is VR? It's U, my U minus V out. Right? So that is VR. So now I'm going to write the currents. The currents there. In that node. So I'm going to call this IR. So what are the currents coming into the node? Currents coming into my node here, U minus. There is no current coming in, right? They're all coming out. So if I write the currents coming out, so I have I coming out plus IR plus I minus equals 0. But I, as you were pointing out, is related to I in, because now I have a current source. And the way I defined this current here was the opposite sign of I in, right? So I, on that node, as I defined, because that's what we choose, is minus I in. Yeah? Plus IR, now comes the over, IR, that is going to be U minus, minus V out over R, plus I minus, which is equal 0. Okay, let's zero out the things that we know that are 0. We know U minus is 0. We know that I minus is 0. Rules of the amplifier. That gives us an equation that leaves us with minus V out over R being equal to I in, which means that V out is going to be minus I in times R. And when we do V out over in, the gain, V out over, typically we write here V in, but in our case the source was a current source, is equal minus R. Now, this is called the trans-resistance amplifier. Why? Because your input is current, your output is voltage. So when you do the gain, the relationship between input and output is resistance. So it changes the output. So current comes in, you measure voltage. Yeah? Okay, quick question. Because I want to do one more circuit before we go.
Why do we keep the negative sign on DR instead of moving it to the other side?
I'm sorry?
How come we leave the negative sign with DR instead of moving it to the left
It's
side?
just the way I defined. So if I had defined I, because I keep making things the opposite so you get used to it. If I had defined I like this, then KCL would be different. I would still get a negative result. Okay? All right. One more example before you go into the world. And then I had here, when I posted, I had a very cool example that I get to if there are not many questions, but you guys ask lots of questions, which I like. So I encourage you to take a look at the example that I have on my slides on the artificial neural example, okay? It's very cool. Okay, last example here. Let's check for negative feedback. So to check for negative feedback, you write your circuit without your independent voltage sources, which are this one. Okay, now this one, to check for negative feedback, you have to be a little bit more careful because here there is a dependent voltage source that is given to you as minus VF. Okay, so I am connecting now U minus to minus VF. So you have to pay attention to this. Okay, so the question I have for you, is this in negative feedback? Let's see. Yeah? Yeah? Confident that it is? Well, we have to take a look. Where is our V out? Our V out, we would measure V out here, right? It's missing here in this circuit. We would measure V out here. We have V feedback. So if I wiggle V out, which is here, that means I am increasing the output. If I increase the output, what happens to VF, which is right here? Increases. If VF increases and it's the same here, right? Minus VF. That means that I am inputting a larger number into my negative terminal. So what's going to happen to my next V out? Decreases. Yeah? How do I know that? Well, because the V out is still related to U plus minus U minus. And if I make U minus larger, that means that U plus, the output, or U plus minus U minus, will be smaller. Okay? So it is in negative feedback. If it is in negative feedback, that means that we can do the fast analysis, use golden rules, and do the analysis for this circuit. Ask your question.
I noticed that the voltage source in the bottom is negative 1.
Uh-huh. Yeah.
And then we'd be subtracting a negative. So wouldn't we be making U plus minus U minus larger?
Yes, you're right.
Okay.
So that means it wasn't a negative feedback. Oh, they caught a very good thing that I must have forgotten. There was a minus here. Thank you. There was a minus here. Okay, so what does that mean? It means that this one is increasing. V feedback is increasing, but this is negative. So I'm making something that is even more negative here. Yeah. And then that means that it's not in negative feedback. That's why my next slide, we have it flipped. So now we know what to do. You flip it, right? Because of this negative. From the beginning, I told you, please pay attention to this. Okay, thank you. Now we can do the analysis. I was going to do the analysis and show that I was wrong. Okay, no, it's okay. Better that way. Okay, so which questions I should ask you? What's important? We know that the V feedback is related to the voltage divider, right? By now, we look at the circuit and we say, okay, I know what VF, voltage feedback, is, which is R2 over R1 plus R2 times V out. And this is what I was saying. Okay, if I increase, for those that were not following, if I increase V out, that means that V feedback is going to be increased, but V feedback is negative here. And we had a negative terminal there. Now we flipped. Okay, that means now that when we do U plus minus U minus here, we have a larger number in plus, and then we are subtracting there, and we are going to reduce the output. Very good. So, golden rule number 2 tells us that U plus equals to U minus. So, what is U plus? Negative VF. What's U minus? Same thing, or connected to something else. V in. So now we know that V feedback, which is the voltage divider related to the resistors, right? We put the resistors there in order to have this feedback, is negative of V in. Okay. So I'll write very